Hello, in this video I'd like to talk about three different types of transformations: dilations, rotations, and reflections. So let's talk about the first one. Let's talk about dilations. A dilation is really like a scaling. It's a stretching or shrinking of a figure. So suppose we want to look at a unit square, the unit square. So we'll have vertices as follows. And let's label these four vertices A. This is the point over 1 up 0. We'll label that B, C, and D. So this is over 0 up 1. And of course A is our origin. If we apply a dilation by a factor of 2, that means that we're going to have our unit square scaled by a factor of 2. And so each kind of vertex here could be thought of as a terminal point of a standard position vector, and it's basically multiplying each of those vectors by a factor of 2. So that gives us a larger square, 2 times as big on each side length. And so we have our new vertices C prime, D prime, and so forth. So the question becomes, how can we encode this in a matrix? How could we do this efficiently? So let's take a look at the matrix calculations. So let's encode the vertices of our unit square. I'll call that matrix S for square, and we'll put those vertices in here as columns. So here's vertex A, vertex B is a 1, 0, vertex C is 1, 1, and vertex D is a 0, 1. So that's vertex A, B, C, and D. And this action of multiplying by a factor of 2, or dilation by a factor of 2, can be accomplished by 2 times S. So this gives a dilation by a factor of 2. And we can see that coming out of the matrix calculations, because if we did 2 times S, that would just be multiplying each entry by 2. So that gives us our A prime, our B prime, and our C prime, and our D prime. It gives us those new vertices, and we see those coming out as the vertices in our square when we looked at the geometry of this problem. So, this idea of a dilation can be thought of as a scalar multiplication type problem. Similarly, a dilation by a factor of k is simply, k times your matrix, or you can multiply an n by n identity matrix times k. In this case, it would be a 2 by 2 identity matrix times k, and that gives you your dilation by a factor of k. Okay, the next transformation we want to talk about is a rotation. So when we're talking about a rotation, we're talking about the following. So let's look at rotations. Let's say we start with our unit square again. And we'll label our vertices as we did in the previous problem. So let's say we take our unit square and we want to rotate by a factor. Say we want to rotate by theta equals pi over 4. And when we say rotate, we'll assume that the positive direction is the counterclockwise direction. So let's make a note of that. Positive direction is counterclockwise. Okay, so if we draw what the rotated figure would look like, our square, if we pick this up and rotate it by 45 degrees or pi over 4 radians, it would look something like the following. Let's put this in a different color. We'll still have side length 1 on each of our sides of the square, but the figure will be rotated. So there's A, there's B prime, there's C prime, and there's D prime. And the question is, what are those coordinates? How could we make that more precise? So the way we can accomplish this is via a rotation matrix. So let's say rotation by theta can be accomplished by the following: a matrix cosine of theta, negative sine theta, and a cosine of theta. All right, so let's use that idea for our unit square. So if we want to rotate the unit square, and we said that the unit square is our matrix S given by 0, 0, 1, 0, 1, 1, and a 0, 1. We want to rotate the unit square by theta equals pi over 4. What we need to do is we need to multiply our rotation matrix times S. So our rotation matrix is cosine pi over 4, negative sine pi over 4, sine pi over 4, and a cosine pi over 4. So what would that calculation look like? Well, if we recall a little bit of trigonometry, cosine pi over 4 is root 2 over 2. And same thing with sine. So we have a negative sine, root 2 over 2. And matrix S consists of the vertices of the unit square. And when we multiply that through, we get our new vertices. Our new vertices end up looking like 0, 0. So there's our A prime. In the next column, we get a negative root 2 over 2, root 2 over 2. So that's our B prime. Oh, I think I have my column switched. Sorry about that. Let's put the correct column here. This is root 2 over 2, root 2 over 2. That's our B prime. And for C, we get 0, root 2. And lastly, negative root 2 over 2, root 2 over 2. So those give us the vertices of the rotated unit square. Let's go back to our picture here. So in this picture, B prime is at root 2 over 2, root 2 over 2. C is 0, root 2. D is at negative root 2 over 2, up root 2 over 2. And A prime was still at 0, 0. Lastly, let's talk about reflections. And there's various type of reflections we could think about. I'm going to talk about 3 in this video. So one type of reflection, we could talk about a reflection over the x-axis. So suppose we have our unit square. And if we reflect over the x-axis, we would get a unit square, but now we get that down here in quadrant 4. Similarly, we could look at a reflection over the y-axis. So let's look at a reflection over the y-axis. And reflection over the y-axis, again, we start with our unit square, but now we're reflecting over y, and so we end up with the unit square here in quadrant 2. And lastly, we could look at a reflection over y equals x. And if we did that, that one's not as exciting with our unit square because we pretty much end up with the same figure, right? So we're reflecting over this line y equals x, and we just get the same unit square back. Let's talk about the sort of matrix representations of these reflections. So the reflection over the x-axis, that is given by the matrix 1, 0, 0, negative 1. Reflection over the y-axis is given by negative 1, 0, 0, 1. And a reflection over the line y equals x is a 0, 1, 1, 0. So let's take a look at an example where we do two reflections. In other words, we form the composite transformation. Now keep in mind that these transformations act like function compositions. So suppose we want to do things in a particular order. Suppose we want to do number 1, we want to rotate by pi over 4, and then after that we want to reflect over y equals x. And we'll do this on the unit square. So if we take a look at what needs to happen, here's our unit square. I'll put that way over on the right. So it's a 0, 0, 1, 0, 1, 1, 0, 1. Okay, so this is our unit square, which we've been calling matrix S. So the first thing we want to do to that is we want to rotate by pi over 4. So to rotate by pi over 4, we have that matrix from our previous calculations. That would be cosine pi over 4, a negative sine pi over 4, and we know what those values are. And so this is our rotation by pi over 4. And then layered on top of that, kind of the last thing we want to do is we want to do this reflection over y equals x. And so that looks like 0, 1, 1, 0. So we could work through these calculations. If we multiply these matrices, let's see what we would get. So this is our reflection. So if we work through these calculations for the first matrix multiplication here, we get a 0, and then we get a plus sine pi over 4. And then the first row, second column, we get a cosine pi over 4. Bottom row, we get a cosine pi over 4 and a negative sine pi over 4. And then we multiply that times our unit square. And working through that calculation, we get the first row times the first column is a 0. First row times second column, that gives me a root 2 over 2. Continuing on, I get a root 2. And lastly, I get a root 2 over 2. For the second row, we get a 0. We get a root 2 over 2. We get a 0. And we get a negative root 2 over 2. So what does this tell us? That tells us that the new vertices will be given by these columns. And if we actually went through and performed the transformations that we were told to perform, we start off with our unit square. Next thing we do is we rotate by pi over 4. So here's our A, here's our B, our C, and our D. Now here's A, here's B, here's C, and here's D. And then lastly, we reflect over the line y equals x. And so if we take this and we reflect over our line, y equals x, A will still be at the origin, C will be over here, so this is over root 2 up 0, so that's our new C prime. Where is B? B got reflected. That's actually still where it was because it was right on that line, y equals x. And vertex D is over here.